Welcome back. So we're at the third session. Okay, so I'm going to share the screen. Okay, so we have, where are we? So we have actually computed the integral of functions by using Gauss quadrature. We have written a very simple kindergarten level code, like very simple script. Just one for loop, definition of some arrays for order, blah, blah, blah. So I want to show you something now. Like if you want to write a function, how would you turn something into function? So I'm going to take MATLAB back, like again, new script, okay? So it's going to be like, we just write function, and then whatever we want to return, we just define it inside, I don't know yet, is equal to the name of the function, Gauss points, let's say GPT, I don't know, whatever it is, or let's make it Gauss quadrature, and parentheses, like I'm going to put some arguments here, okay, and add the function. So this is going to end it. So inside this, I need to do something, whatever it is, blah, blah, blah. For something is not going to work, I guess. So I don't know what is it. Maybe this Gauss. We'll see. I don't know. Something wrong. First thing is like it should get actually like as a like NGP maybe inside. Like NGP is going to be a parameter, like which order I like to pick. Okay. So this is going to be the function. So I'm going to take all of this here for inside. And it should also return the value of actually it's going to define the Gauss weights and Gauss points for the corresponding order, correct? So it should actually return two stuff, Gauss points and Gauss weights. So this is going to return this. But it's going to depend on the NGP actually, correct? So depending on the NGP, for now, very simple. Just the first basic thing like to, for conditioning is just if, else. So say if, for example, NGP is equal to 2, okay, something like I'm going to just define this stuff, okay. So else NGP is equal to 7, I'm going to define this. But what if this should be else if, correct? Because this is again checking something, but else like it didn't hold any, like it is not 2, it is not 7, because we haven't defined that yet. There's also like other possibilities like switch function, but let's just use for now the if function. So what's going to happen? If that is the case, so I can just write break because we don't have this defined yet. Break is going to just take out this, okay? And this is the else if end, so I need to add one more end to enter function and save the function with the name of the function as is, okay, to the same folder. So save it as Gauss quad M, okay, save it, close. Then I don't need, I guess, this stuff. First comment, everything. So what should I do? I'm going to define actually NGP myself. Let's say NGP is equal to 2. And then I'm going to call so I'm going to call the function, which is Gauss quad function with input argument at GP. It should return me this, I guess, Gauss weight and Gauss point. Let's see if it's going to work. I'm not sure. Just I'm doing everything spontaneous. I don't use the MATLAB a lot, but let's just run it. And if there's an error, there's going to be a sound by MATLAB. So you'll see the problem. So there's like error. So it says break statement appeared outside of a loop, use return in set. Okay, just let's use return. Return is going to return nothing, I guess. Let's go back to the function. Well, there is something wrong with this. So let's do nothing for now. Maybe just return. Save. So this is my function. I can't control something. Let's check it again. So it is 0. Something wrong. Do you think the integral was 0 before? I don't think so. Let's check the Gauss points. Oh, the order is wrong. Okay, so so the order of this is going to be changed, because if you see the function, the first is going to be the weight. Let me just see here. Wait. Let's just open the function again. Like we said, the first is going to be Gauss point, then Gauss weight. So you should use the same order. Okay, so either change this Gauss weight, Gauss point, and a close, and this should work. Oh, something check missing extra characters. Where is it? Line 5 of, maybe I need this one. Oh, this is, I just want to remove the 7, for example. Okay, let's come run. Yes, now correct, it works. So this is now called the function. So I don't see this anymore here. Okay, so it is somewhere in your routine. Okay, I have just a folder containing my subroutines. You can call it like this is just one of the subroutines as a function, and I can just contain everything inside this function. Like if you want to go up to order 256, just put here and use it in any problem, any code you like. Okay, so this is going to be just written once, and you're able to keep this and just use for later problems. Okay, so this is actually going to give us, okay, the required Gauss weights and Gauss points for any order we like. What if I write 5? It shouldn't work. So what I have now, because we haven't defined the Gauss weights and Gauss points for rule number 5, the function returned nothing, and it couldn't be able to define Gauss weights and Gauss points. So it didn't continue, actually. I couldn't find the Gauss weights. Okay, so it's not going to function. So that's why like these kind of stuffs are important in terms of like coding. Maybe like you should also print screen some stuff for the user. But the idea is like in this class or in our research, we are not developing this kind of stuff for general users. So it's for ours. So we always know what to put inside. I know I need to define either 2 or 7. Okay, I can just increase this number. So like, for example, I go back to let me go back to the POMAX. I want to include maybe like number 3. Okay, copy this. I'm going to just modify this thing. Else if NGP is equal to 3, test. That's it. So I'm going to take Gauss weights. Here is equal to Gauss weight 2 is equal to. Just I do it once and use a lot later. Okay. Gauss weight 3. And this is Gauss point 1. And this is Gauss point 2. Semicolon, Gauss point 3. So now we have defined everything. Correct. It should work for 3 as well. Save, close. Now, if I just change this NGP to 3, it should work. But there is error because 3 is not as accurate as number of Gauss 0.7. Okay, the error is maybe, I don't know what was the other result. Let me just see. Okay, so I have copy here. Let me just, how can we do it actually? Let's compute the error. Let's say I'm going to do this twice. Okay, so I1 is equal to I. Okay, and I'm going to change this thing to 7. I compute another I. I2 is equal to I. And I want to see the error between the two, relative error. So let's say I1 minus I2 divided by the correct values actually. Add 2 times 100 is going to give you the relative error. Let's say RE is equal to, and I need to multiply this with. So let's run this. So what I have 24, almost 25% error if I use 3 gas points compared to 7. Okay, if I just decrease to 2, the error is 60%. Okay, so if I wanna, what if I increase this a bit more? Okay, so it's gonna take time if I take the 0.8. Let me just, but I'm going to anyway. So it's just fun. Let's take this. So I want to see like what is the difference between the two. So what I do is I go back to my function, and I now define the else if ngp is equal to 8, rule 8. So a bit of modification, sorry for the time. So this is 1, this is 2, this is 3. Take this here. 4, 5, 6, 6, 7, 8. Semicolon, 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 semicolon. In Turkish, this is noktalı virgül, but it is semicolon in English. It sounds like we have a little bit different translation. It's actually maybe yarım virgül. If you make a chicken translation. So gas point 1 is equal to, let's comment, yes, now 2, 2, 3, 3, 4, 5, 6, 7, 8. I hope everything is correct. So we have now gas quad function, which actually defined 4 orders, 2, 3, 7, 8. Everything is saved.
There's an additional minus at the beginning.
Yes.
Of the...
Thanks. This one. And now correct. No, one more.
Actually, they all have.
They are not negative.
Some of them.
Minus, just okay. I see. This is not minus. Now correct. So if you just write down one of them, like with a positive sign, it's not going to work. So I'll show you in a minute. So I just close this, take my function. So let's see the difference between 7 and 8. This is 7. This is 8. What is any guess on the error? Idea? Run. No, it's like 10 to negative 5. So you see like the 7 and 8, like I mean the result changes at the like order of like the digits are like 10 to negative 5. So it's quite correct to use the NGP 7 instead of 8. But if you go like to 3, let's make it the lowest is 2. Now it is going from 6, it's like 60%. It's a lot of error. And this is not like absolute actually. Maybe I should take absolute value of this thing to make it all positive. Oh, what's wrong? It is absolute. I2 is negative. Okay. Absolute of everything, actually. Yes. No, it's negative. I don't know. What's wrong here? Oh, it's correct. Okay. I just. Okay. Anyway, so it's a relative error in percentage, like a 60% error if you used to. But let's just change the function, like as I said. What if this is just a x cube? Okay, I said x cube is going to be correct, exact, if I use 8 or 2. So what should you expect in terms of error? 0, correct? Let's check. It's infinity. Why? Because I have a 0 by, like, I2 probably is 0. That's why make it x cube plus x square. So x is GP. I mean, the value of the integral is 0, so something divided by 0 is going to give infinity in MATLAB. It's not undefined, so let's try this. 124 was wrong. Oh, okay, because we didn't change the function in the upper part. So I need to also change this one and check again. Yeah, like 10 to the negative 14. So this is just I mean, this is the numeric error in the computation. That's it, like very small. Okay. So it means like either using 2 or using 8, doesn't matter if if we use the correct number of order, if the function is polynomial. But if it is not polynomial as before, I need to increase the number of Gauss points and weights, like maybe 7. As we see, it is, I can make it more complex, I guess, if I just multiply this with like. But anyway, I mean the idea is simple. As long as you know your like external force given, and if it is complex, like a lot of variation in the domain of interest, then I need to increase the number of integrations. But the integrals resulting from the FEM systems that we're going to solve was like they're going to be all polynomial, at least for the approximation of the unknowns. So the 7 rule should be enough, I guess. Okay. So any question up to now? No? No question? So this is the lecture one. So if you don't have a question, I'll go into details. Like more theory, okay? Like I may go a bit fast, like maybe like we're going to go ahead of the syllabus, but we're going to have more time later in terms of application, because I want to show you like the full implementation in terms of like the developing a simple solver. So what if you like, I'm going to continue actually with the very first example of approximation. Okay. Do you have any question? No? Yes. No from here. Okay. Select from the participants. Question? No. I guess.
I think.
Okay, so I got one no, so let's continue then. This is going to be what? So we have actually learned a little bit of implementation for simple coding in terms of integration of one-dimensional. So I'm going to actually continue later with the integration of different boundaries. Like what if I have an integral from 0 to 1? It's not going to work. This one is not going to work. We need to mapping. Like we need to map actually. Maybe next week I'm going to do like each maybe lecture I'm going to give you some little stuff like this. So I'm going to show maybe later in the class how we're going to modify if I have different boundaries of integration from -5 to 6, for example. It's not going to work. I need to have also mapping from one domain to another. So it's going to require you to multiply that with the Jacobian stuff, like mapping from X real space to integration space. But later, okay, not that fast. So let me just continue. So in FEM, we find approximate solutions to the model problems. Okay, so this can be anything. Like this can be like a Navier-Stokes equations of motion to find the pressure distribution around airfoils, like the drag force around a car. Doesn't matter. This is going to be, and the governing equation is going to be a partial differential equation, multi-dimensional one, doesn't matter. Okay. And FEM is a numerical technique, so it is going to find an approximate solution. So what do we mean by approximation? Okay, and we're going to start with a very simple example. So our very first example is the following simple differential equation. So we go like I'm going to define a model simple problem. So just a mathematical equation, no physical meaning. You don't have to do like we don't have to worry about the physics in this class much. So the differential equation is going to be, let's say, this is the d square f over dx square negative is equal to 1. So this is a common like example I used for the very first example for omega, which is valid between x is equal to 0 and 1. Okay. So this is a second order equation. So I need two boundary conditions on f. Like the boundary conditions are going to be f0 and f1, which are the boundaries of my domain, have to be defined. So let's make it 0. So it says like this is going to be like f is a function varying in between 0 and 1 with the boundary conditions like values 0 and 1 at the end of the domain 0 and 1. And what is the, I mean, I can solve this equation actually. So we're going to first find, okay, let's find first the exact solution for comparison later. Let's find, I have almost 20 minutes. I think I can finish. Let's find the exact solution by integrating in x twice. So just take this. So what is it? First integral is negative df over dx is equal to x plus an integration constant. Another integral is negative f is equal to x squared divided by 2 plus cx plus the second integration constant. And CD can be found by applying the two boundary conditions. If f is equal to 0 at 0 and 1, 0, 0, d is equal to 0 first. If it is 0 at 1, what I have, 1 over 2 plus c has to be also equal to 0. That means c is equal to negative 1 over 2. So that means my f is equal to negative a half x. Ooh. Let's make it positive. No, actually negative x square minus x. I guess this is the solution. So this is the actual the analytical solution. So now the idea is like because like this is an approximation, like FEM is kind of find an approximate solution. So how can we approximate the f? So there are various ways. So the problem is actually this one. This is my governing, like this is my differential equation defining the, like this whole set of equation. Boxed differential equation, we know it is the analytical solution. And the reason, like I show here, the exact solution is just for comparison later. So what about, what if we assume f is approximated by some function, I don't know. Let's say f of hat, like this is the approximate f, I don't know. It's the form is like a times sine times pi x, okay? Like we just usually like call this as like the approximation function. Like we can also show this like a times pi x, okay? So this is like a shape function or approximation function and a coefficient, I don't know what is it. So if this is the approximate form of the f, So what can we do without, like, if I don't know how to solve this kind of, like, I'm given a differential equation, but I don't have the exact solution. What can I do? I can just put the f back inside the differential equation to find actually the unknown, correct? So, but how am I going to find the evaluate a actually? So there are various ways, like imposing the, so we are able to, actually we can impose f by various ways. Okay, so these are, the first one is collocation, collocation. The second one is average technique. And the third one is Galerkin. So I'm going to take now this Galerkin into box, green box. Okay, so FEM uses Galerkin. Okay, that's why I'm going to, like, this part is kind of like showing you why we use Galerkin. So what are these, like, by one? Okay, so collocation is actually doing this. It's enforcing the imposing actually. So impose, let's say f double prime hat negative at some collocation point is equal to, like, it's going to satisfy the governing equation. Like, this is my governing equation. So there's like at some collocation point. What does that mean? For example, my domain is in between 0 and 1. So why don't we like impose? Okay, let's satisfy at 0.1/2. Okay, so for example, if x is equal to a half, that means like the second derivative of my approximate solution is going to satisfy the differential equation. So what does that mean? So what is f hat second prime? So the derivative of f hat with respect to x is equal to what? What is the derivative of sine pi x times a? Cosine pi times a times cosine pi x, and one more derivative is negative, correct? So it's like going to be negative pi square a back to sine pi x. So that is the second derivative. And I want this to be satisfying this equation. So this is going to help us to find the a. So I know this is going to be equal to -1 from this equation. That means find the unknown a in the approximation. How? So if this is the case, what does that mean? Cancel the blah, 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 blah. A is equal to, oh, that is the xc, sorry. Oh yeah, at the collocation at xc. So a is going to be what? 1 over pi square. If you put a half here, what is sine pi over 2? 1. Correct? So it's 1 over pi square. So that means for this case, my approximate solution is 1 over pi square times sine pi x. Now, I didn't solve the governing equation. So I didn't integrate, but it says, okay, this is, so let's compare in the MATLAB. So how am I going to plot this function? So I define first nx from, so I have 11 minutes, 0 to 1. So I divide this into maybe 100. Okay, so that's how we define like just an array of x. So if I want to plot my solution, actually, like let's plot x comma the function itself. What is the analytical solution? I guess it is this one, -1/2. So I need the MATLAB. Where is it? Okay, so point -5 times x squared. So now there's the quotient. You need to use dot here because x is an array, so you cannot take the power of an array in MATLAB. So if you want to take the scalar, I mean the powers of each individual element, so you need to use the dot power of, okay, and minus x, I guess, correct? And if I want to plot this now, let's see, plot is going to show you this. This is the exact solution, okay? Now I want to hold on this and plot the approximation. Okay, so I have 10 more minutes. So hold on is going to plot the other function onto the same figure. So now I'm going to plot the approximation, which is x comma a, which is 1 over pi square. So this was the a times sine pi times x, I guess. And let's plot it with the dash line. Now, I got some solution. It looks like the function, it is not exact. There's a difference there, of course. Okay. So the dash line is the approximation by collocation. Okay. So now I'm going to show you another method. Average. What if, like, instead of like just doing this, I use the average technique. So here, let me just use average. Okay. Imposes the average of the equation over the interval. Like instead of like picking one collocation point, we do this. Why don't I then integrate my equation? Like I have f double prime, which is x negative. So this is equal to 1. So integrate this from 0 to 1 dx. Integrate 0 to 1 dx. Okay, so this is going to help us to find the a, but by imposing the f as an average. Okay, so now I'm going to have like integral 0 to 1. Negative is going to be a times pi squared times sine pi x dx is equal to integral 1 dx. Okay, 0 to 1. So what is the result? So this is the x. What is the integral of this? X. So we don't actually like you suppose you don't know anything about the integrations. Let's go back to kindergarten. We go back to our MATLAB code. We have already written this. Okay, so why don't we just compute this? Change everything here. I want to see I. So what I need now? I need an integral of 1. Just change it to here 1. There's no function. It's just 1. What is the integral of 1? It's just let's increase this to 7. It is 2. Do you think it is 2? If I integrate 1 from 0, 0 to 1 dx, do you think this is correct? And what is the integral of this? It is x from 0 to 1. Yes, what is it? It's 1. So what's wrong? It's not going to work because the, yes, it's not going to work. So, okay, you don't know this yet because this integral from 0 to 1, I need to multiply with a half, I guess, everywhere. The Jacobian is here. I'm going to teach this later. This is just 1 over 2, I guess, Jacobian here. I need to multiply with the Jacobian as well everywhere. Okay, run. It should be 1 anyway. What about the other function? Let me come back here. It's a pi squared, just pi squared times sine pi x. So let's make it here. Pi squared. That's pi squared times sine pi times x is Gauss point. I hope it is correct. Let's compute the integral. It says it is 0. I don't think it is. Oh, a pi square. What's wrong here? Sine pi x. Jacobian is actually correct. Oh, okay. A lot of stuff. I need to also multiply this with a plus b over 2. Because x is going to be converted. You don't have this yet. Let me just check here. Oh, there's something wrong. What's wrong? So I have 5 minutes to finish this. There is going to be an x, which is going to be a half Gauss point plus b a half. This is the, okay. Okay, I need to multiply this with x. This is x actually. Should not work. Yes, I guess that is correct, I guess. I'm not sure. 2 over pi, 2 times pi. What's wrong? Pi square. This is actually b. This is x sine. Oh, this is pi x. Oh my god. Okay, I'll check. Now correct. Okay, this is actually 2. Yeah, it's 2 pi, I guess. That's the correct result. No, that's correct. So what I found is 2 pi for this integral is equal to 2 pi a is equal to 1. That means a is equal to 1 over 2 pi. Okay, so the average is actually gave me this one. With this one f hat, like I used called like average maybe, I have 1 over 2 pi sine 2 it's pi x, I guess. So what was it before? Oh, it's pi squared. So let's see the difference now. Now I will hold on and plot. This time, instead of pi, I have 2 over pi, correct? 1 over pi, 2 over pi. So it's just this one. Okay, it's 1 over 2 pi. Correct. Okay. Now instead of this, I'm going to take now this to 2 pi and just this time plot it with dots. And where is the figure? I guess it's here. Where is it? Up, 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 up. I don't see it. One. I don't think it is. Let's see plots. I have 2 more minutes to finish. So just okay, let's start with this one first. This is the exact solution. But doesn't because we change x, okay. Because we didn't clear everything. So x, I need to redefine x. This one, plot x, this is the exact solution. Hold on. Plot this one for the collocation. Hold on. Plot this time with the average. So what I get, actually, I have something like going above. So it's kind of like we're limiting the exact solution from above and below and above. Like there's kind of like it is in between. And the third method is going to be somewhere in between, which is going to be Galerkin. And I'm going to show it in the next lecture, I guess, because we're almost finishing the time. Like I have like almost 1.5 minutes. So it's going to be later. I'm going to show you how am I going to get somewhere closer to this curve. So I got something below and above something. So we're going to get almost somewhere here by using the Galerkin technique, which is going to be the next week. So I'll start with this next Galerkin. So it can be Friday. So I'm going to inform you for the next lecture. If you have any question, please do ask. Question? No? Okay. So if you don't have a question, I'm going to stop sharing and recording, and then I'll see you in the next lecture. Not see, but at least maybe here. Okay, so bye-bye.